Okay, yeah. So we start to talk about regression, right? Regression is when that we have the y belongs to real number, right, or some numerical values, right? Okay. So depends on the problem, right? Depends on the problem that we want to solve, right? Sometimes that we may have this kind of situation, right? Such as that if we want to predict like a weather, right, like a temperature, right? Okay. If we want to predict like a I think the real problem is real problem sometimes. That for instance, if we want to predict raining, okay, so we can choose to try. Let's say we try classification, raining or not, or we can try regression, how much rains, right? I think we can try that, right? Okay. I think you probably uh, find out that based on the weather channel, right? I think you may have the sense like when the probability of raining when it's higher than 30, so they say it will rain, or maybe in the real case it will rain, right, like that, or maybe you feel it's raining, right? Okay, so there will be some kind of hidden threshold, okay, like you have to find out. So then if we talk about we want to find a good model here, right, for the raining prediction, then if you try regression problem first, right? If you try to use regression to solve the problem, then later on, the second stage is that you have to find out the threshold to decide when the result is higher than some value, we call that raining, right? Lower than something, we say it's not, it may not rain, right? Like that, okay? And also, so that's one, right? And also when we talk about sometimes, okay, we are going to study a probabilistic approach. Probabilistic approach means that we are using probability, right? So probability is what? Between 0 and 1, right? Okay. So sometimes, okay, not so soon, but later we're going to discuss probability, right? Okay. Then probability is numerical, right? It's not like 0 and 1, right? Okay. It's between 0 and 1. So sometimes what we want to predict is not y here, is probability of y equal to 1. So that would be what? Between 0 and 1. Okay? That case is also what? Regression problem. You got that? So all kinds of, you know, very, a lot of fancy problem for us to solve, right? Okay? For the last one, I want to emphasize again. So sometimes even it's classification problem, but we choose to predict. Maybe I can just write here, right? Make sure that you. So sometimes it's a classification problem, but what we want is to predict, okay, yi, okay, equal to 1, right? Want to predict this one. Then it's what? It's become like we transform a classification problem to regression problem. You got that? So there are so many different choices, right? In fact, that for all the things I just mentioned, classification and regression, and make classification to be regression means that we want to predict probability, right? Okay, for these three things, later there'll be some matching methodology, okay? Some methodology will match these three categories, okay? Yeah, and for this one, we want to predict probability, right? Later, we can introduce logistic regression, right? Okay. Yeah. So yeah, but that's for later. So which means that the regression problem, the methodology belongs to regression. There will be more than just one kind. Okay, there will be many things belong to this category. Okay. So in the old days, right, people talk about interpolation, right? Interpolation, uh, given, I mean, this one is interpolation, right? Interpolation means that we just simply we want to go through the data points, all the data points. So regression interpolation may not have, or may not care so much about, the any kind of, So we may not care that says the meaning, right? So maybe, or maybe some kind of meaning hidden behind the scene, right? Maybe we just care about, the curve is smooth enough to go through all the data points, right? Yeah, it belongs to something else. Okay, yeah. So we can choose. So in the old days that we talk about polynomial, right? Polynomial interpolation, right? So, and also we can use it for the time series prediction. Means that what we want to predict is the future, right? So in this case, usually we call that extrapolation. Yeah, if it's recording, then that doesn't sound good. Hold on. Hello? Yeah, I hope it's okay. I didn't check the recording. Maybe it doesn't record anything, right? Then I'm not going to in trouble. Well, all kinds of problems. I think it's working, right? Just not so loud. Anyway, yeah. So we talk about interpolation, right? Then, whoa. Then just like what we say, right? So there's an error function. Usually we call mean square error, right? So that's quite common. So if you heard about MSE, right? So that's the thing that we mentioned here. Okay, so it's numeric. So it's numerical. So that means that we are going to measure the difference, the square difference, right? So meaning that we don't care about, like the prediction is, higher than the true value. Okay, like the thing that we may experience in the classification problem, right? So let's come back. Okay, so when we have W0 and W1, right? So we're going to, let's say we can draw a service, a service. The service could be like this, right? Like this. Okay, I cannot easily draw the service. It will be like a ball, right? Okay, so why? Because we have W0 and W1, right? When we write down the whole thing is quadratic, right? Okay, quadratic. I think it's not that difficult to imagine that the surface is like a ball. Okay. Yep. So if you project into any kind of direction, that's a quadratic curve, right? Okay. Yeah. So quadratic curve means what? Means that quadratic surface means what? Means that there's only one single minimum. Okay, one single minimum. That's the local minimum and also global minimum, right? So which means what? Which means that if we want to find the best answer, that will be the best answer for sure, right? Okay, how? Very easy. We just randomly try to go as low as possible to any kind of direction right? If we can try to make the W, I mean, we start to some kind of W, right? Okay, we try to search for its neighbor, right? To make a W to be W0, W1, to be either larger or smaller, which means the 4 directions, right? 4 direction, one of them will give us what? Lowest value. And lower than the value that we have now, then we try that direction. And we try that for several steps. In the end, we are going to reach this one. That's what we call what? Gradient descent, right? Gradient descent. Gradient descent, right? Yeah, gradient descent. My writing is better than this one, okay? Yeah. Anyway, so in fact that you know for the linear regression, right? We can always find the best answer, right? I can just simply give you some I think some of you may heard of this one before, right? Okay, yeah, because what I need to write down is more than just a few words, right? So I cannot write in that way. So we're talking about, let's say, it's up to, let's say if we have x1, yeah, if the function is like what? If function is like this, right? Okay, maybe we can start from 0, right? Like this. Okay, so we are going to have what? We are going to have W0. Okay, so here, suppose that's the first data, right? So in the end, what we want is to make sure that this one is Y1, right? Or maybe Y1, right, in this notation. So now we have the same, but from the same feature, but from the second data, right? Okay. So the last one, suppose, is m of them, right? Okay. Yeah. So that's what we hope, right? So in fact, that this should be what? Should be like what? Okay. We hope they are close enough, right? But may not be the same. You got that? Okay. If it's equal, that means what? That means, you know, more like this case, right? You will go through the data points. Okay? Yep. Any questions? Yeah. So now that we want to write in matrix. So now we want to write in matrix. Okay. So we are going to write what? In matrix, that means, first of all, there's a W matrix. Then there's a, sorry, it's not W, right? W is actually is here, right? Then that's Y. Okay, so what we need to write down here, that will be like x1. It's not that easy to see from here. Okay, so we are going to write down like what? 1, right? Then x, 1, 1, x, right? Then the last one is like this, right? Okay? Then the second one is like this. Yeah? So here is the matrix like what? The dimensionality will be m by, right? So this one is m by 1. And this one is m by 1, right? Like this. Yeah? Okay, so we are going to write what? We're going to write x. Sorry. Yeah, that's called the A matrix, right? How about that? Okay. If I write x, means you may feel like it's a variable, right? Okay. Yeah. Okay. Again, it's not really equality, right, is more like this, right? Okay, yeah. I mean, if we can really find something to make it equal, right? I mean, that's perfect, right? Usually, but that's not the case. Okay? You probably will think, okay, we are going to solve that's what kind of W will make the thing to be equal, right? Okay? You're not going to think about that, say, no, right? Right, why? Because this one may not be a square matrix, right? Okay? Got that? Yeah, so this one is not possible. So, yeah, so this one is not possible, right? But what is the magic is that actually we can do something to make, we can do something, how to do something. So we can try to multiply both sides by the transpose, okay? A transpose. So everything becomes like this, right? Like this. And we can really find W to make this to be equal. So in the end, it's like what? In the end, it's like, okay, W's actually can be chosen to be what? To be inverse, okay? Like this. So this is not derivation, no, okay? It's like the direction, like what we think, okay? Actually, it's like some kind of way to memorize the whole thing, right? In fact, that the derivation should be what? The derivation should be, okay, we just choose this one, then we know this one is true. Should be the reverse direction. Okay, the logic should be like this, right? What I try is not the logic direction. It's try the thinking direction. Okay? Yeah. So choosing W to be A transpose A inverse times A transpose Y, then we can get this one. If we can get this one, okay, if we can get this one, they may not be too different, okay? In fact, I mean, that's another story, right? If we choose to be like this one, we can prove AW and Y is as close to each other as possible, okay? Yeah, so that's, so the whole thing is this one. The whole thing is, yeah, so that's normal equation, right? I mean, actually, the whole thing is normal equation. Okay, then the next thing to discuss is that, okay, so now that we talk about linear regression, right, which is simple, right? In fact, that it doesn't need to be linear, right? In fact, that we can try to, write some other things. I think it doesn't need to be linear anyway. So, but the next thing is that, okay, if we think the linear regression is not good enough, right? Then such as like this case, right? Then we can do something else. I mean, maybe we should do something else. We can try higher order polynomial, right? Okay, but how high, right? So we can try from degree 4 to degree 15, right? Then which one is the best model? Which one is the best model? Okay, before now we talk about how to evaluate the result. Okay, based on, for instance, we can try to evaluate like the model variance, right? Model variance, or maybe you can call that stability, right? To make sure that, okay, degree 15, for instance, is not a good model, right? Then we come back to this one, right? Okay? But it's not that easy, even that we know, based on our visualization, we know degree 4 is the best, right? Or we check the stability, right? But the problem is what? When we don't have time to try all this, right? So painful, right? I mean, how can it be possible that we try a degree from 1 to up to 15, then we decide that degree 4 is the best, right? So usually it's not that trivial, right? Okay. But as an explanation that I show you that, stability or, the variance, model variance will be something that we have to pay attention to decide the best model, right? Okay. So again, so we have to remind ourselves the assumption. Assumption is something before we try any kind of parameter estimation, we search for the best model. What is the assumption? Okay, here could be linear, could be degree 4, whatever, right? Okay. Usually, to decide the assumption is harder than, deciding the best model. Okay, so that's something you have to keep in mind, right? Okay, once that we decide the assumption, then the rest is trivial, almost like the normal distribution, normal equation, right? It's kind of trivial. Yep. Yeah, so then model selection. Model selection is usually translated to how to find out what could be the best model, right? So which means that we also need to consider, hypothesis space, the assumption, how to choose the best assumption, right? Okay, so we talk about bias, right? The bias, yesterday, right? We talked about bias. So that's the bias, what we call more carefully, that usually more precisely that we talk inductive bias. Inductive bias means that the bias that is necessary to be introduced so that we can solve the induction problem. Okay? So why? Because the learning problem is ill-posed, right? Learning problem is ill-posed. Given, again, just like what we say, data to model, right? Data to model is not one-to-one, right? It's not one-to-one, right? One-to-one means everything must be deterministic, right? Given whatever input that you have, the same input, we should always get the same output, right? But that's not exactly the case. When we have the same data, we always have the same model. No, right? Okay? So that's why we say ill-posed, right? Okay? Ill-posed means that it's not really a problem, a mathematical problem, right? Because we are not going to solve the problem like ax equal to y when the a is singular, right? So then we are going to run into some problems, right? So ill-posed, okay? After we introduce inductive bias, meaning we assume a hypothesis class, assume a hypothesis space, then everything will be what? Will be clear that we can get single solution, right? Okay, that's very important. Yeah, so just like a rectangle case, right? We assume is a rectangle, right? Okay. Then the rest is easy, right? Okay. Then we still have to find out that, okay, the later, we need to think about the model, how to call that a model is a good model, right? It's not just to feed the data, it's to generalize, okay? So later, that's why we're going to try cross-validation. Yeah, cross-validation is that we only give, let's say we have 100 data points, right? We choose some percentage, okay, to train our model, then use the model to predict the rest of the thing that was not included in the training data, right? Okay. Yeah. So based on the cross validation or something like this, right? Visually, that we can also check, right? Okay. In this case, how to run cross validation? Yeah. Suppose we want to use cross validation, choosing a partial subset out of the whole set, right? To train the model, then if this model can predict the rest well, right? Then we say, okay, it passed the cross validation. Okay. so that we know the model is good enough, right? Okay, so how to run cross validation in this case? Can anyone give us some comments here? Anyone? How to run cross validation in this case? So you understand Chinese? Really? Okay. Perfectly or just? Yeah. Okay. We shouldn't say something bad about you in Chinese. Yeah. So he said that okay, we choose maybe if we try tenfold cross validation, right? Tenfold means what? Tenfold. I better to use the computer more often, right? So that tenfold is like we have, let's say 10. The data will be chopped into how many parts? 1, 2, 3, 4. Yeah, like one. The 10 parts, right? Evenly, right? Okay. Maybe we choose 9 out of 10, right? Like those, or this, right? We use this to train our model, then use the model to predict this part, right? Okay. Then we try 10 times. We can even try many times. Meaning what? Meaning we try some other partition, right? Okay, some other partitions. Just assume we fix this partition, right? So we are going to build the model 10 times, okay? Then we calculate the average, right? The prediction result, how different between the prediction and the truth, right? Okay. So in this case, that we are going to select maybe 9 out of 10 data, right? To train our model, which means that maybe this point, right? Maybe this point, maybe some other point were not included in our training data. Those will be used for prediction, okay? Actually for validation, right? Okay. Then if the result is good enough, then we say, oh, this model is good, right? So if we check this one, I think very easily we know the result will not be so good, right? Because let's say when we remove this data point, we want to predict, or maybe some other points, right? We know it's going to be bad because a lot of ups and downs, right? So it won't be good, right? In fact, that the difference will be between the truth and the prediction could be a lot, right? Okay, so cross validation in this case. Any problems? Any problems? So one problem I can easily say to you, maybe you don't really pay attention to, is that if the whole thing is the x-axis is time, okay? X-axis time means what? You need to tell me, are we going to dealing with not just a regression problem, right? We want to find the best model for sure, right? But what we want to predict the future, right? We want to predict the future. So building the best model, then what? The best model means that we can predict the future well, not the past, right? When we try the cross validation, we try to predict the past, right? Could be like we select this data point. We don't select this data point. Then we build a model, we try to predict these data points, right? And that's the past. Who needs that, right? Okay? So depends on, you need to be very clear that what kind of application that we are thinking, right? We are dealing with. If we want a model that can predict the future, right? Don't try tenfold cross validation in this case. Meaning what? Meaning that we should always try, use the past data to predict the future. The past data to predict the future means that we should go the other way around. Maybe we start from this window size. We use this window to predict this data, right? Then we can use another window, sliding window, we predict this one, etc. to see the model is good enough. Suppose we try the same strategy, right? Okay, so very different, very different. Depends on the application. Either we are dealing with, the forecasting model for the future, or, what we just discussed, the temporal consolidation doesn't always, like meaningless, right? Because sometimes we want to not like predict the past. Sometimes we just want to do imputation, right? Imputation means what? Imputation means that sometimes you can think about those as like still you can think about the x as what? As time, right? You can still think about that. But one way is that x is really not time, right? It could be like some geographic x, right? Okay, meaning that assuming here and there, right, there'll be sensor readings, right? Then sometimes for some sensor it's malfunction, it's not working. We use rest of the sensor to predict, right? So that if we can do a good job, right, then we don't need all the sensor to be always working, right? Okay, so that's one case, right? Another case is that if the x is time, right, then what? We can assume like the sensor may not be always on, right? Sometimes the sensor can go to sleep for a while, then come back. Go to sleep a while, then come back. To what? To save some energy, right? Okay, sometimes for the Internet of Things, right? Maybe we have to take care that the sensor can be last for quite a long time, right? So we have to make sure that the sensor will not use a lot of battery, right? Okay, like that. That's all. Okay, so all kinds. I think I talk about all kinds of the strategies and also some thinking that you have to keep in mind when we are dealing with real data. Okay? Any questions? Okay, so I think you probably already experienced that what I teach you is not something that you can easily find it from some textbook, right? Okay? I teach something that usually I try my best to teach you something that you cannot easily find from the public domain, right? You can find it, but not easy, right? Okay, so that, yeah, I hope that you can get that, right? Okay, then here we talk about underfitting and overfitting. Yeah, so underfitting is, the hypothesis less complex than the function, the true function. Then overfitting is the other way around, right? Overfitting is the hypothesis too complicated. Maybe we don't have to have such a very complicated model, right? Okay, so we already talked about this one. This case is underfitting, and this case is overfitting, sort of, right? Okay. Yeah, so you can think about that. So I think some people get confused, like maybe I can choose something right here. Yeah, suppose this one is the complexity. Okay, complexity. So model complexity, right? So we can choose a simple model or more complicated model, right? So usually what we have is, okay, for the simple, when we go from simple model to complex model, we can see the y-axis, the arrow, right? The arrow will continue to go down, right? Okay? Yeah. If we focus on what? If we focus on the training. Okay? So if you still remember that for the tenfold course of validation, right? Yeah. So this part is the training error. Okay, we used 9 out of 10 to build a model, then predict this part of the blue area, right? Then that's the training error. Okay, then this part, okay, so that's the validation error. So validation error sometimes will be like this: go down, then go up after certain point, right? Okay, yeah. So meaning, so here is test error, maybe validation. I think I can change to draw like this. Maybe after a whole semester, my skill will be better, right? Yeah, it's better, right? Yeah, validation error. Okay, so so overfitting is this direction. Okay, here is overfitting, meaning what? Meaning after these data points, right? So when we can enjoy better and better, I mean smaller and smaller training error, but the validation error goes up. Okay, meaning what? Meaning that this kind of complexity, we don't need that. It doesn't help us because model is too complicated, right? The data is not so difficult to understand. Okay. On the other hand, this direction is underfitting. Okay, is underfitting. Yeah. So some students will get confused. They always say, "Oh, overfitting means okay, the validation error is larger than the training error." It's not. It's not. Okay, don't get confused. Right? It's more like this area is overfitting. This area is underfitting. Any questions? Okay, the end. So the triple trade-off. Okay, from time to time we are going to find out something that we can control. Okay, one is hypothesis complexity, right? The amount of data. Okay, then given these two, right? Then what we want to say is that okay, when we want to focus on generalization, means that we want to predict the future, right? Okay, we want to predict something on the fresh new data, right? Then we are going to say, okay, given let's say more higher and higher complexity, right? I mean, what is that? Okay, anyway, so when we increase the model complexity, right, the generalization error will goes down in the first part, then goes up after that. Okay. Yep. And this one means that simply gives us like when we have more and more data, right, the generalization error will be smaller, right? I think you can understand that, right? That's something that we learn from what? PAC learning, right? Okay. Yeah, so that's all for this part, right? This one is another related, but later we're going to focus more is that after all, right, we learn here is supervised learning, right? So supervised learning is actually quite like active for decades, but now people shift to unsupervised learning more, right? How and why? So Yang LaCun actually made this comment, right? So he say supervised learning, unsupervised learning, and reinforcement learning is like what? So supervised learning, I mean, when is the last time you have a cake? So supervised learning is the icing on the cake. Okay, The unsupervised learning is the cake itself, right? The reinforcement learning is this one. Okay? Why is he said that? He said that when we receive one data, right? Okay? If we focus on supervised learning, then this data, what is the most important part? Why, right? Why the target value, right? Okay? Usually it won't be too much, right? A few bits, right? Per sample. But the unsupervised learning, we pay attention to what? The X, the attributes, right? There'll be a lot of them. Okay? Millions of them, right? Okay? A lot of information. So he said that why we should focus on a small piece of information but forget about a lot of information. That's what his comment, right? And also, a lot of people work on reinforcement learning, meaning that playing chess, right? Playing chess is like what? After we play for a few steps, then we know which one wins the game, right? So the only information after several steps, there'll be 1 or 0. Too few information, right? The information is so small, right? Okay, given such a very small piece of data, right? Piece of information, we hardly get, can draw a lot of, meaningful conclusion, right? So that's something we have to be careful, right? So before now, people work on reinforcement learning, playing chess a lot, so many, right? Like AlphaGo, right? And also supervised learning, right? So he say we should spend more time on unsupervised learning. Okay, yeah. So that's what his comment. I remember one time that I mentioned this comment to some researcher. Okay. Apparently they are from different groups. Okay. Young LaCun is from where? Where? Young LaCun is from where? Facebook, right? Okay. Yeah. So, but another guy is John Lanford. Before now, I think he's in Google, right? Okay. What's the difference? Google and Facebook, of course, they're not the same, right? Yeah. So Google pay more attention to what? What? Google. Online advertisement, right? Which means what? Click-through rate, right? Click-through rate, right? Click-through rate. Okay, meaning that they show you some advertisement, how likely that you're going to try to click that and then buying something in the end, right? Okay, that's what. Okay, the online advertisement is related to reinforcement learning. In the end, after a lot of advertisement showing you a lot of advertisement that you could click through so many different steps, in the end, buy it or not. That's what they care, right? Okay, so they care about reinforcement learning, of course, right? So John Lanford actually at that time, right? I don't know. I didn't check his recent position, right? At that time, the John Lanford say, "Oh, reinforcement learning is very important, right? Given what? Given the real world applications, right? A lot of applications like that, right? And also, so you can imagine that in our real life, so many problems can be transformed to what? Reinforcement learning problems, right? For a lot of things, like you study here you study hard, right? So you cannot be away that you go out to play basketball, right? You cannot. Why? Because in the end, you want a good grade, for instance, right? Or maybe later, for your career, you want a good position, right? So, sort of, right? So it's reinforcement learning. Okay. Yep. So many things belongs to reinforcement learning, right? Meaning that we don't really get the true answer right away, right? Okay. But Young Raccoon is from Facebook, right? At that time, at least Facebook now is also good do some, online business, right? But before now, it's more like doing what? They try to, predict that. Okay, before now, they try to predict, okay, who on the photos, right? Like that, right? So that's supervised learning, and also unsupervised learning means what? Facebook before now they pay more attention to what? Deep learning, right? Okay. So on the other hand, for the Google, they probably don't just work on deep learning, right? They work on many things. Okay. Yep. So that's all for this part. Okay. So yeah, maybe we can take a break right here.